Okay, now welcome. So we're going to do the first proof, the first part anyway. I'm going to split this up into a couple of videos. So the proof of this lemma, we're going to start off by going through this part right here. It says let R be an echelon form matrix, okay, and consider its non-zero vector rows. First, observe that if we have a row written as a combination of the others, for example, let's say we have some row vector that's written as a linear combination of the other rows. Okay, and so we have C1 R vector 1 plus all the way up to R sub I minus 1, this term for I minus 1 plus this term which is I plus 1. Now, just so you know, because we have this in terms of all the other rows, so we're not obviously including that, because if we did, we would just move it over here and combine like terms. So it's not going to be included in here. And then we continue on until we get to the last term. Okay, so let's say we have a non-zero row that's written as a linear combination of the other rows. Then we can rewrite this equation here to be this one, right? So we have a zero vector because all we have to do is just move this over to the right side and we get this vector equation, right? The zero vector. So, and then all we have here is C1 R1 plus all the way up to C I minus 1 R sub I minus 1, and then here's our ith term, right? So that's where we moved over, and then the rest of them, right? So basically we just moved this over, and all of the coefficients, where all the coefficients are, oops, not zero. That's a mistake. It should be not zero, not zero. Oh, okay, I'm sorry, no. Yeah, we're not. All the coefficients are there. I misread it. Okay, so specifically we know that not all of them are zero because this is -1, right? Because we had R sub I, so the leading coefficient here was 1, right? So this C sub I right here is -1, right? Because when we moved it over, we had to subtract. So just so you guys see that. Okay, so now we have this equation here where not all the coefficients are 0. Okay, now the converse also holds, because if we start out with this equation here, right, where not all the coefficients are 0, then we can express that vector as a combination of the others by just moving it over to the left and dividing by the negative C sub I. So we could start with this and we say, okay, well, what if, let's say this coefficient is not 0? Well, we can write this vector R sub I as a linear combination by just moving it over here and then dividing by negative C sub I. And then we could do that. So the converse also holds. Okay? So therefore we have proved the theorem if we show that in this equation here all the coefficients are 0. And so for that we're going to have to use induction on the row number I. Okay, and so that's what we're going to start doing in the next video. We'll start doing the proof by induction, and we'll start with the base.